Right, so we introduced the Poisson process as a dynamic process with continuous time as the index of the process and the process value as a function of time, representing the number of events or arrivals by the given time. So the process starts at some initial time t0, which is time 0, and then at some random time, the first event occurs, so our process being the counter of the events stay at 0 until the first event and then jumps by 1 at the arrival of the event. Then until the second event happens at some time t2, the process stays at 1 and then of course jumps by 1 again, and then the process stays at this level until the arrival of the third event when it jumps by 1 again, and so on. You can express the count mathematically in several equivalent ways. The easiest one is to write it as the sum of the indicator functions, where this expression inside the summation takes value of 1 if the expression in the subscript is true and 0 otherwise. For example, if we are counting the event up to this point, so imagine this is the location of our small t. As t1 is smaller than t, the indicator function returns 1 for t1 and so on for t2 and t3. However, t4 is not smaller, so the function returns 0. So you can see adding these indicator functions indeed gives the number of events before time t. As t moves to the right, of course, more of the indicator function will return 1, so the count will increase. Also, notice this is one realization of the stochastic process, so the events times will vary from one realization to the next. So we should actually be writing the count as a function of the path, which we represent by W. A different path, which is a different realization of the stochastic process, will produce a different count as one would expect. And we also shifted the time index to the subscript to save space. One more thing, when we move to discussion of counting or random measure, you will see this indicator function written in terms of Dirac measure, which really represent the same thing as you can see. So this expression in terms of our indicator function can be represented as follows. So you can see it's just moving the subscripts and arguments here and there. You will see this Dirac symbol a lot in the discussion of random measure, so I had to mention it here, though we don't need it here. Now, the word process might suggest that the use of the time interval in the index is inevitable, because we normally associate the word process with something that's evolving over time. However, a more general definition of the Poisson process is as a collection of points in the spatial or space sense. So one doesn't have to restrict the settings to a count over the positive time axis. So let's get rid of the count from the origin and the time axis. And you see we got a random collection of points. So instead of sequential events, this could now represent the locations of trees at one given time. The axis now represents space, one-dimensional here. So think of x-axis. Say we are counting trees along the road. We can represent the location of the points by a sequence of xi's, just like we had ti's before. And this sequence is random because the location of points will vary from one realization to the next. And we have now an example of a point process, Poisson point process to be precise, as the point processes can be of other types such as binomial, negative binomial, etc. But we are interested in the Poisson process here. And we need some measure of count. So in the temporal dimension case, which is the case where we had the time as the dimension, we had the count of events from the origin. Here, again, we can count the number of events and any interval of interest. Let's say the left and right endpoints of this interval are A and B. Then we can easily count the number of points in this interval. And in the temporal case, the intensity per unit time was lambda. So we had the lambda times t to represent the intensity measure over interval from 0 to t. Here we will have the intensity per unit length, and the length of the interval is then just b minus a, which is the same thing as the Loubet measure if you want to go technical. So the number of events in this interval will follow Poisson distribution with parameter equal to lambda times the length of the interval. Now this representation can be easily generalized. We can make it two-dimensional. So we can view this as a random collection of points in some area. These could be trees in a forest if you like, or the location of animals, or the centers of the cities as viewed on a 2D map, or the position of the households of the people who have coronavirus. The location of each point will now be described by its position along the x-axis and y-axis. So the collection of points is like a sequence of a two-dimensional variable, random sequence, let me remind you. And we can now talk about the number of points in, say, a rectangular area. So taking lambda as the intensity per unit area, the equivalent of lambda times t is now lambda times the area of the region, which we represent by b. And you would know that Lubac-Maja has the same interpretation of size here, area as opposed to length. And you can go 3D, then area will become volume. But now the points can represent the locations of the galaxies in the universe or the locations of the stars. One can add the time dimension as well. For example, the density of trees in a forest or of cars on a motorway changes over time. So we see, once we understand the basics, generalization to higher dimensions is relatively easy, and we can thus go back to the two-dimensional case. Now so far, we have assumed homogeneous process. This the intensity, or what you might call density, is constant across space or time. But there might be good reasons for the density to vary across space. For example, some areas might be more fertile than others, or in the case of counts in temporal view, say rainfall vary by the time of the year. Here we have introduced a complicated looking pattern, but the heterogeneity can take simple forms. For example, increasing in one dimension. Say you're looking at locations of trees in mountainous region where the mountains get steeper as you go from left to right and the density of trees decreases. Anyways, in such situations it will make sense to make the density a function of location. What it means is, previously we said the number of points in a rectangular region B had Poisson distribution with parameter equal to lambda times the size of the region. Now density is not constant, so to determine the intensity measure for this area, we will need to take integral of lambda over the region. Here I have written just the one-dimensional version, but you can easily make it two-dimensional, or 3D if you like. Or in the temporal or time-dimensional view, we said the intensity measure over the interval t is equal to lambda times t. But if we say the intensity varies over time, then it will just be the integral of the intensity function as a function of time over the relevant time interval. And we can easily verify that if we substitute constant lambda inside the integral, then the integral will evaluate to lambda times t. So we can easily see the difference between the non-homogeneous and homogeneous Poisson processes. Notice the increments of the non-homogeneous process are not stationary, reason being they depend on t because lambda depends on t, but they are independent. By the way, one can easily transform the non-homogeneous process into a homogeneous process via time change, a technique we will see a lot in this series later on. So non-homogeneous case is not much harder, assuming one knows how lambda varies across space or time. But in most cases of interest, the functional form of lambda will not be known, so a more convenient approach is to assume lambda is a random variable. In the most basic case, you can say lambda takes two values, say lambda 1 and lambda 2, with probability p and 1 minus p, and you get what's called mixed Poisson process with parameter, say lambda. It's not a Poisson process, by the way, but a mixture of Poisson processes, mixture of two Poisson processes here. The lambda 1 and lambda 2 are the values of a random variable, so let's represent the random variable by capital lambda. Now, if you agree not to worry about mathematical niceties for now, then the lambda of the mixture process will just be the expected value of this random variable, essentially lambda 1 and lambda 2 weighted by their respective probabilities. And of course, the mixture doesn't have to come from just two processes. One can have the lambda random variable taking n values, and the resulting lambda will then just be kinda probability weighted average of the n lambdas. One can then go infinite dimensional and say lambda is a continuous variable. One common example is to assume lambda is gamma distributed with shape and scale parameters. The resulting process will be negative binomial. Another common example is to assume lambda follows log-normal distribution. Such processes are widely used in the modeling of the number of insurance claims, by the way. Now, as we alluded to earlier, the resulting process is not going to be Poisson. For example, we said if lambda is gamma distributed, then the resulting process is negative binomial. Conditional on the value of the lambda, the process is Poisson, but the mixture of these conditional Poisson is not Poisson. To see, let's quickly calculate the mean and variance of the process. You know for Poisson the mean and variance are equal, so our plan is to show they're not equal for the mixture process. Let's explain with time dimension. Remember, count of events over time. This is just to keep things simple. So for the mean, we need to calculate the expected value of the number of events. Easiest way to do this is via the iterated expectation, or Tower property of expectation. This is far simpler than it looks, by the way. Assume we have been asked to calculate the average of the integers from 1 to 5. So to calculate the average, we just add the integers and divide the sum by 5 to get 3. Now suppose we condition on another variable that divides the list into two sublists based on whether the integer is below 2.5. If we calculate the average of these averages now, we get 3. Notice this is probability weighted average, where the probabilities of the two sublists are 2 divided by 5 and 3 divided by 5 respectively. And this is what the iterated expectation is all about, but of course it applies in more complicated settings. And now we know, conditional on lambda, the process is Poisson. Remember, the processes we are mixing are Poisson, so the conditional process being Poisson is a more technical way of saying the very same thing. And we know the mean of this Poisson process is just lambda times t, and we will leave it in this form. Let's move to the variance. We will now use the total variance formula. It's like the variance version of the iterated expectation. So these are like Adams and Eves. By the way, the total variance is called Eve because it is E of V plus V of E. So mnemonic is Eve. To visualize this formula, let's reuse the same example of the integers from 1 to 5 and calculate its variance now. The mean, as we saw, is 3, and we can calculate the deviations of the points from the mean and then square them, and then the average of the squares of these terms will give the variance. Now let's use the same conditioning that divides the list into two sublists. We can calculate their respective averages and then calculate the deviations from the conditional means. If we calculate the two variances and then average them using the probabilities as weights, we get the first term of the variance formula. Now in this case, this variance will be smaller because the deviations from the conditional means are lower compared to the yellow bars we saw before. But then the conditional means are different from the overall mean, so you need to add their variance and you have the second part of the formula. The conditioning variables can be different. For example, it might be that the conditioning variable divides the list into different groups, say it groups 1 and 5 together and the rest into a separate group, and you can verify that the formula works. Now we know that conditional on lambda, the process is Poisson, and we know the mean and variance of Poisson are equal, and they're equal to lambda times t here, and we will leave it in this form. Now comparing the mean and variance, we see the variance of the mixture Poisson has got this extra term, which is not going to be 0 unless lambda is constant. So we deduce that the mixture Poisson is not Poisson. Its variance is larger than its mean. You may recall this property is called over-dispersion and is a desirable property in modeling many real-life examples because many of the processes one encounters have more variance than the Poisson process will imply. One can generalize the mixed Poisson in a slightly different way. Say there are fixed regions within the space. We only show 3 regions for the sake of simplicity. The lambda is constant in each of the regions but random, so it will vary from one realization to the next. What we are saying is that the overall space is heterogeneous but is divided into homogeneous set of regions. We don't know what value lambda takes in each region, but we know the distribution of lambda. Now you can see we can go a step further and make the lambda a stochastic process, and we will get a doubly stochastic process, which is also known by the name of its introducer as Koch's process. It's probably easier to visualize this process in dynamic view, so let's consider the time view. We have 2 stochastic processes now, the lambda and the arrival events or points. Let's consider the simple case in which lambda just jumps between 2 states. Of course, the jump times are stochastic. Suppose it starts in the low intensity state, so the events are sparse. Next, it jumps to the high intensity state, so event happens with more intensity now. At some random time then, it goes down again and the events become sparse. It then jumps again and we are in the happening state again. It then jumps down and the events become rarer. Then it jumps again and the points get cluttered. The reason for making lambda a stochastic process could be because the random variables that we assume in the mixed Poisson case vary over space or time. So it is like a non-homogeneous generalization of the homogeneous case, but in the stochastic sense. Previously, we had constant lambda in the homogeneous case and a deterministic function of time in the non-homogeneous case. Now we have random lambda in the homogeneous case. Remember the mixed Poisson we just discussed, and collection of random variables or stochastic process in the non-homogeneous case. The stochastic intensity process might be unobservable. For example, the number of breakdowns of a manufacturing process could vary because of the quality of the input material or environmental factors. In financial applications, the doubly stochastic process has been used to model the securities that are subject to default risk. Say, the default process is driven by the company financial conditions and the macroeconomic environment. So this is the process describing the hazard rate, and the point process will then be the default event. So the higher the hazard, the higher the default probability. So you can say the doubly stochastic means a stochastic process running in a stochastic environment, which is practically what real life is, right? Though real life processes can be a bit more complicated. By the way, many people consider the mixed Poisson as doubly stochastic process as well, though it is, as you can see, at most a simple case of doubly stochastic. Now, what other generalization can we consider? To see, let's bring the Poisson probability. So we started by generalizing T, by which I mean we really changed the positive part of the real line to a multidimensional space. We then went to town with lambda. Making it a deterministic function of time produces the non-homogeneous process. Making it a random variable leads to a mixed Poisson process, and making it a stochastic process leads to the doubly stochastic process. So we have touched everything except the variable representing the meaning of the number of points. So let's consider generalization along this dimension. Remember when we derived the differential equation for the Poisson probability, we assume that only one event can happen in a small time interval. So in terms of our spatial generalization, it essentially means that the process represents the count of points and we will have at most one count at each location. Assuming we are considering a 2D view, so we have a plane that we saw before, and let's say the points represent the locations of trees, and the locations are represented by the sequence of a 2-dimensional variable, the dimension being the 2 axes. Now each tree is going to be different. We can say there are 2 types of trees, where the type could be defined based on age, say old and young trees. Let's say we represent the new trees by green color. So what we have now is called a marked process. So with each point is associated a mark which represents its type. So each element of the sequence now consists of location and mark. In terms of probabilities, consider a rectangular area. So we can say the probability of the number of points in this area follow a Poisson distribution, and then depending on the realization of the number of points of each type follows a binomial distribution. The key to simplicity is to assume that the distribution of the marks is independent of the count of points in each location. The mark could be a continuous variable, say the size of the tree. Some trees are bigger than others, and we can say, for example, the sizes are log-normally or exponentially distributed. So Poisson gives the number of points in each area, and then the size of each point is randomly distributed according to some probability distribution. It can represent things other than type and size if one likes. For example, assuming the points represent the locations of stars in the universe, the marks could be the brightness of the stars. Now let's consider a few special cases that are of interest in many applications. One can use the marks to generalize the Poisson process from simple, which means at most one event can occur in a small interval, to compound, which means there can be more than one event. The marks in the marked Poisson process becomes multiplicity of events in the compound Poisson process. Essentially, there are multiple things associated with each arrival. So a simple Poisson process gives the arrival times of the events, and then conditional on the arrival of each event, we have an independent random variable which determines the number of points associated with each arrival. Think of this as a way to represent the arrival of people in groups of different sizes. So we can accommodate for the possibility of Kim and her 3 followers now. Previously, in the simple Poisson case, we represented the value of the process over time, which is the count of events by a given time, as the sum of the indicator functions. So the count increases by 1 at each arrival, or the process value jumps by 1 at each arrival. We can represent the value of the compound process in a similar way. Now the size of the jump is a random variable, which we can represent by y. One can write this in several alternative forms. For example, it really is a sum of random variable, but the number of terms is random, the random thing being the capital N and the upper limit of the index, which follows Poisson distribution. It sounds like a complicated process, but if one assumes y is independent of the arrival process, then the analytical treatment is quite simple as long as one doesn't assume a complicated probability distribution for y. We shall encounter this process in a future video. The y, which is the multiplicity or jump size, could be discrete variables such as binomial with say m equal to 10, or it could be a continuous variable, say gamma or log normal. In insurance, for example, the number of insurance claims could be described by the simple Poisson process, but then each claim will be for a different amount, say a grand or maybe a million. So this is a use case of compound Poisson process. And financial derivatives, the Merton model extends the Black-Scholes diffusion model by incorporating jumps. It kinda assumes log-normal distribution for the jump sizes. And you would also know the Lipton type models, which adds jumps to stochastic local volatility models. So they are real applications of these things. Now one can take this further with a view to generalization. One possibility is to view the multiplicity as a cluster of points. So the Poisson process produces the centers of the clusters, and within each cluster we can have a random number of points which are randomly distributed. Essentially, we have the parent process which produces the centers of the clusters. Call these the parent points, and then usually an independent process that gives the number and locations of the points in each cluster. Call these the child points. So each cluster will consist of a random number of randomly distributed points. The child points don't have to lie on the center, and for good reasons the centers might be unobservable as well. So the key is the locations of the centers and the distribution of points around the centers. There are two very popular variations of the distribution of points in the cluster. Neyman-Scott processes result when one assumes the points are independently and identically distributed, and you can see this specification can easily generalize to higher dimensional spatial space. On the other hand, one can prescribe the distribution of points in terms of inter-arrival times or distance between the points, and one gets the Bartlett-Lewis process. As you can see, generalizing this process to higher dimension is going to be tricky. These cluster processes have a large number of applications. For example, this could be used to model the locations of people who are infected by a viral disease. So we have the locations of the primary cases as the centers of the cluster, and then the cluster of the people they infect around them, or the location of defective parts in a computer system, or the parent process could be the locations of the centers of the galaxies, and the offspring points could be the stars in those galaxies. The cluster models are also widely used to model rainfall, by the way. As another generalization of the compound Poisson process, one can assume Y is a stochastic process. A more specialized case of this possibility is the filtered Poisson process. Let's explain with a classic example. Say you're monitoring the flow of water in a river. Now, where is the water coming from? Maybe rain somewhere higher up in the mountains. So let's say we capture the rain events with the count of thunderstorms. So the Poisson process is giving you the time of the thunderstorms, and with each thunderstorm will be associated a different amount of rain, and we let Y represent the amount of rain. Now the amount of flow in the river at time t will be the results of all the thunderstorms that happened before, but not all the water will arrive at the river at time t. So to capture this, we just define some function of the variables that gives the response of the river to the past thunderstorms. We can represent the response by W. This process is called filter Poisson process. An example of this response function could be the exponential. So Yn is the amount of rain associated with the nth thunderstorm, and its contribution to the flow in the river at a later time will decline exponentially with the length of time. Of course, this is slightly simplistic settings, but you get the idea. So are we done? Considering we have covered all of the parameters in the Poisson density formula, so probably yes, but actually not. One can also consider a generalization in the sense of properties of the process. For example, the simple Poisson process is a counting process, so the value of the process increases over time, and hence the process is not a martingale. We know martingale property is very important in analysis, so one can consider making the process a martingale, which is very easy to do. All you have to do is to subtract the mean from the process, and the resulting process becomes what's called Compensated Poisson process. Let's see the details. Let's bring back the simple Poisson process visual we saw earlier. So it is just the count of the number of events over time starting from the origin. Now we know that the expected value of the Poisson process is lambda times the length of the interval, essentially rate of arrival per unit time times the length of the time interval. So the mean increases linearly with the length of the interval. Now what happens if we subtract the mean from the process value? The average part is easy because changing the sign just reflects the red line along the x-axis. For the stochastic part, we just need to add 1 to this line at each arrival time. As we have marked the jump times on the x-axis, we can remove the step function. So from the first arrival time, we shift the red line upward by 1. We do the same for the second arrival, so the process value after this arrival will be 1 higher, and so on for the next arrival. We can get rid of the bars now and just add the filled and open circles. Remember, this is the right continuous with left limit property. The process is not a step function now though, as you can see. And now you can convince yourself that the compensated Poisson process will have mean of 0. And by the way, the variance has remained unchanged, so it will be lambda times t. And if you divide the process by lambda, then you can see the variance will be equal to t. Mean of 0 and variance of t, remember, is the Brownian motion. So as you increase the jump intensity, the distribution of Poisson process will approach the distribution of Brownian. Right? So I hope you enjoyed the video, and I look forward to seeing you in the next.